Dear students and viewers, you are welcome to this video lecture. In this video, we are going to look at set and number system. In the set and number system, we are going to look at partitions, and we have partitions. Sets. We begin with partitions. Partition. What is a partition? So we begin with we say let S be a set. A partition of the set S is a collection so let's write it as P of non-empty subsets of S. It's a collection of non-empty subsets of S such that, or satisfying one. We write P is equal to S1, these are subsets, S2, S3, up to the last element, say SR, where R is the last number, is the last element of the set. 2, that SI intersection SG is equal to empty, and this is I not equal to G. Two distinct sets are pairwise disjoint, and the collection, so you see that the collection, the union of S1 union S2 union S3 the union of all the sets up to SR is equal to P. Remember we said non-empty sets, non-empty subsets. So each SI is non-empty. So once a set, this collection satisfies this, then the collection is said to be a partition for the set S. Now P is a partition for the set S. Take for example 1 in this lecture. So let S to be equal to 1, 2, 3, 4, and 5. So consider these subsets A, or let me say S1 is equal to 1, 2, S2 is equals to 2, S2 is equals to 3, 4, and then S3 is equal to 5, just a singleton. Therefore, P, this the collection here, S1, S2, and S3, this collection is a partition. Of the set S. It partitions the set S. How? Because S1 intersection S2 intersection S3 is equals to what? Empty. Meaning the intersection of all the sets is an empty set, because 1 and 2, you cannot find 1 and 2 here. You cannot find 1, 2, 3, 4 here. And so you cannot find 5 here. And so, the sets are pairwise disjoint. Secondly, this is just one. Secondly, we test the second item. And what is the second item saying? The second item. So the union of all, so S1, union S2, union S3 is equal to what? So we have a set now. S1 is 1 and 2, union S2, this is 3 and 4, union S3, which is equal to 5. And so the set here forms S. The union of all the sets gives us back S. Now, another example, example 2. Consider the set S to be equal to the set containing A, B, C, and D. Now, and also let S1 be equals to A, B, C. Let S2 be equals to say C, D, and then S3 to be equals to a set containing only B. So you see, these three subsets are actually non-empty, which they satisfy the first condition, which we have stated here in the definition. It's a collection of non-empty sets. So this is a collection of non-empty subsets of S. Now, what are we going to test? So we test 1, their intersection, and see. So you see S1 intersection S2 is equal to what? S1 intersection S2 is C. It's a set containing C. So you see, if you test and find out that even two pairs are joint, meaning they are not disjoint, meaning they are connected by one element, then it is enough to stop and say that S is not a partition. So therefore, the collection here of these subsets, so we say P equals to this collection containing S1, S2, and S3 is not a partition of the set S. It's not a partition of S. Exercise for the readers. Exercise. The exercise is saying which of the following is a partition of S. So where S is equal to A, B, 1, 2, 3. A, a set containing A. So let me put it like S1 is equals to A comma B, and then S2 will be equals to 1, 3, and then S3 to be equals to just 2. And let's have S4 to be equal to 3. So B, S1 to be equals to A, AC, and then so we have S2 to be equals to 1, 2, and then S3 to be equals to A, A comma 3. Then C, S1 to be equals to A, S2 to be equals to B, and then S3 to be equals to 1, 3. So now it is left for the readers to read and tell us which one is actually a partition of the set S here. So now we are going to look at Cartesian product, or the set product. The Cartesian product. But before looking at Cartesian product, we are going to look at ordered pairs. Ordered pairs. Because we know what a set is, and we know how elements of a set are, or what are elements of a set. So suppose we have two elements of a set. So let A and B be elements. Let A and B be in S. These are subsets of these are elements of a set. The pair A comma B is called an ordered pair. It's called an ordered pair if A is regarded as the first element. And B as the second element. So this is an ordered pair. So that if A is the first element, B is the second element, we write the ordered pair as A comma B and not B comma A. So that if A comma B is equals to C comma D, this will happen so that you have so we will say A comma B is equals to C comma D if and only if A is equals to C and B is equal to D. Students and viewers should take note that the ordered pair here is different from the set itself. Whereas in a set, you can have a set this A comma B, and this is equals to B comma A. Meaning the order of the elements in a set does not matter. But in an ordered pair, the order of the elements matter. We are now ready to take the definition of Cartesian product. Cartesian product. Consider two sets. Say let A and B be two sets. Then the set product, or the Cartesian product, of A and B. So we write this as, so it is written as A cross B. So it is also written as A cross B, or you say the Cartesian product of A and B is defined as, so we say A cross B is equals to the order of all ordered pairs A comma B, such that A is in A and B is in B. So we can now write an example. So example, consider this set. Let A be equals to 1, 2, and then 1, 2, 3, and B be equals to x, y. So the Cartesian product A cross B is equals to a set containing all the ordered pairs. So the first element, you see, the first element here is actually from A, and the second element is from B. So you pick element of A and then pair it with the element of B. Pick that same element with the next element of B until you exhaust the elements of A crossing or pairing with the elements of B. And this is how we go about it. So this is, you have the ordered pair 1, comma x, and then 1 with y. So 1, comma y. So we are done with 1. So we go to 2. So we have the ordered pair 2 with x, and then 2 with y, and then we go to the next element 3. So 3 with x, and then 3 with y. And that is the meaning of A cross B here. So let's look at B cross A. So this is equal to, so we start with the elements of B, then the elements of A. So we have x1, so I have x2, and then we have x, comma 3, and then we have y, comma 1, and then we have y, comma 2, so we have y, comma 3. So this is the Cartesian product A cross B. So it is obvious from this very example that A cross B is not equal to B cross A. For what? For one thing, if A is not equal to B. Yeah, if A is not equal to B, so B cross A is not the same thing as A cross B. Students and viewers should take note. And so if A is equal to B, we simply write, A cross A as what? A squared. Students and viewers should take note that A squared, we don't mean you pick the element of A and square it. No. So that A is in A. That is not what we mean. That is not the meaning of A squared. But however, what A squared means here, it means what? The ordered pair A1, comma A2, such that A1 and A2 are both coming from A. But we start with A1, then A2. Alright, look at this example. Take A. So we know our A is equals to 1, 2, 3. So what I have, if you ask me to find A cross A, which we write as A square, and this is something like saying 1, comma 1, I'm picking 1. So 1, comma 2, I'm picking, and then 1, comma 3. Look at it. A is equals to 1, 2, 3. So write it in two places. A equals to 1, 2, and 3. So 1 with 1, 1 with 2, 1 with 3, and then you go to 2. So we go to 2. 2 with 1, 2 with 2, and then 2 with 3. Next, we have 3, 1, 3, 2, and then we have 3, 3. This is the meaning of A squared here, or A cross A, the Cartesian product of A. So, as a concluding remark, we can give an exercise to students. Students should find A cross B and B cross A in each of the following. One, we have A is equals to 1, 2, 3, 4. And then B is equals to 3, and then 3, and then 5. 2, A is equals to A, B, while B is equals to X, Y, Z. Thank you very much for watching our video. See you in the next video.